In this tutorial, we're going to take our discussion of expected value and the mean, and we're going to extend it to apply it to a concept called variance. We're going to find out how the mean and variance are alike. That is, they're both related to a mathematical concept called moments. Before we can do that, we have to talk about some of the rules regarding expected values. Suppose we have two variables, x and y, and they're random variables, and then we also have a constant that we'll call n. Now, this epsilon, this Greek letter e, is not multiplied times x here. It's a function of x. So the expected value of x is the mean of x. This funny looking u is a Greek letter mu, and this subscript x means the mean of x. So the expected value of x equals the mean of x. The expected value of y equals the mean of y. The expected value of a constant n equals the constant n. Now, when we add something together in the expected value function, we can separate them out like so. So the expected value of x plus a constant n equals the expected value of x plus the expected value of the constant, which simplifies to the mean of x plus n. When we add two variables together, it works the same way. The expected value of x plus y equals the expected value of x plus the expected value of y, which turns out to be the mean of x plus the mean of y. When we multiply a variable x times a constant n, the expected value of this expression is the constant n times the expected value of x, or n times the mean of x. So in a sense, we're just factoring out this constant and put it out here. However, when we multiply two variables together, like x times y, it is only sometimes that it equals the expected value of x times the expected value of y. If x and y are independent, that is, they're not correlated, then this equation works. However, if they do have a relationship, they're correlated in some way, it is not true that the expected value of x times y equals the expected value of x times the expected value of y. That is, typically, this is not true, only in this condition. All right, we need to talk about variability. Here we have a distribution. The mean of this distribution happens to be 0. That is, its central tendency is 0, right in the middle. We'd also like to talk about how variable this distribution is. What do we mean by variability? Well, this distribution does not consist of just this line. It consists of every point contained underneath the line. So we can imagine just millions of points here. And we want to know how far are all these points from this line. That is, what is the horizontal distance from each point to the line? So imagine this point right here. We can measure the distance from this point to the line, and then another point, and another point, and another point, and another point. We can imagine all of the points underneath this curve, and how far are they from the line? How far are they on average? This would be a measure of variability. This distribution is narrow. That is, the points on average are closer to the mean. This distribution is broad. Each of the points on average is further away from the mean. So we need some formula that measures the average distance from each point to the mean. Intuitively, it might make sense to just take each value of x, subtract the mean, and take the expected value. But it turns out this intuitive solution doesn't really work. Let's see why. The expected value of x minus the mean equals the expected value of x minus the expected value of the mean. Now, the expected value of x is the mean, and the expected value of the mean is the mean. So we have the mean minus the mean, which equals 0. This will be true for every distribution that actually has a mean. That is, there's some distributions that have no mean. Strange, but true. So we need to find some other formula that gives us a measure of the average distance of each point to the mean. Intuitively, we might think, well, the problem with x minus the mean is that some distances are negative and some are positive. Why don't we just take the absolute value of this distance? And this would be a reasonable solution, except that it turns out that absolute values are kind of cumbersome to work with algebraically, and statisticians have come up with a different solution. That is, they take the square of this distance. And squaring things makes them positive. So the expected value of x minus mu squared has a special name and a special symbol. The symbol is sigma squared. This funny looking O with a hat on it is the Greek letter S, or Greek letter sigma, and sigma squared means variance. The meaning of variance is kind of hard to talk about, but the square root of variance, the square root of sigma squared, is sigma all by itself, and sigma is the standard deviation. The standard deviation represents a kind of average of the distance from each point to the line. It's not an arithmetic average, it's a different kind of average. It's the square root of the average squared distance. We'd like to understand the variance in terms of expected values, and we're going to do it along the same lines that we did with the mean. So as a review, the expected value of a discrete variable, a variable that comes in certain intervals, was the sum of each value of x times the probability of that value. And this will equal the population mean of x. But we didn't have a discrete variable. What we had was a continuous variable. So what we had to do was at first imagine that the continuous variable was split up into bins, sliced this way. And then we had to imagine that the bins got narrower and narrower, like so. So we started off with 2, then a bin width of 1, a half, 1/4, 1/8, 1/16, and they just got so narrow that eventually we got to the idea that the bins were infinitely thin and the sample was infinitely large. And then these bins were sliced so thin that it was like we were doing an integration with calculus, and that we were summing up every very thin slice and multiplying it times the probability, and this gave us the population mean of a continuous variable. We're going to do the same thing with variance. Here we have on the left the value of x, the original distribution, and on the right we have x minus the mean squared. So here's our equation. The expected value of x is every value of x times the probability of x. Likewise, the expected value of x minus mu squared is the value of x minus mu squared times the probability of x minus mu squared. And so we're going to imagine that the bin width is first wide, and then we'll imagine it getting narrower and narrower and seeing what happens. So the range of x is -infinity to +infinity, but shown on this graph is -4 to 4. X minus mu squared has a different range. Because it's a squared value, it's going to always be at least 0. Notice that the most probable values are close to 0, and as we extend in the positive direction, the value becomes less and less probable. So now we're going to imagine the bins are going to get narrower. So they go from 2 to 1 to 1/2 to 1/4 to 1/8 to 1/16, 1/32, 1/64. And so forth. Eventually, the bins get narrow enough that we can just integrate them into a nice smooth curve like this. Now, this distribution started off as a normal curve, and the distribution for x minus mu squared looks like this. It happens to be something called a chi-square distribution with 1 degree of freedom. I'm not sure about this, but I think that the reason that it's called a chi-square distribution is that you've got an x and it's squared in some fashion. Note here that as we get to 0, it extends up to +infinity. That is because when we slice the bins very, very, very thin, we never actually get a 0. So the expected value of x minus mu squared is the long-term average of this distribution. Because this started off as a normal distribution, it is a chi-square distribution with 1 degree of freedom. This brings us to a concept called moments. The first moment of x is the expected value of x. The second moment of x is the expected value of x squared. The third moment is the expected value of x squared. In essence, we've got e to the x to the 1. So we've got a nice sequence 1, 2, 3. Now, there's a different kind of moment in which we subtract a certain constant. The central moments of x are taking x minus the first raw moment, x minus mu, x minus mu, x minus mu. And the first moment, we take it to the first power. With the second moment, we square it. The third moment, we cube it. And we can keep going to the fourth, fifth, sixth power. So these are called central moments, or sometimes they're called moments referred to the mean. We can understand the second central moment, the variance, in terms of the raw moments. So the expected value of x minus mu squared is equal to, if we expand this out, the expected value of x squared minus 2 times x times mu plus mu squared. And then we can separate out each of these three elements to the expected value of x squared minus the expected value of 2 times x times mu plus the expected value of mu squared. Now, because of the rules of expected values, we can take any constant here and pull it out of the expected value function. So this 2, we're going to factor it out. This mu, it's a constant. We're going to factor it out. So this central term becomes 2 times mu times the expected value of x. This value here, the expected value of mu squared, is mu squared because mu squared is a constant. 2 times mu times the expected value of x, well, the expected value of x is mu, so this central term becomes 2 times mu, which in turn becomes 2 times mu squared. Mu times mu is mu squared. So we've got the expected value of x squared minus 2 times mu squared plus mu squared. So we're subtracting 2 mu squares and we're adding 1 back in. So if we add 1 to -2, we get just 1 negative mu squared. So the variance equals the second raw moment minus the first raw moment squared. In the next tutorial, we're going to extend our discussion of expected value in moments and apply it to other aspects of distributions, such as skewness and kurtosis. That is, the first raw moment is the mean, the middle of the distribution. The second central moment is variance, how spread apart is the distribution. What else is there? The shape. If you're already familiar with skewness and kurtosis, I hope that the next tutorial helps you see them in a completely different light.